So the task at hand is to determine how many of these molecules are polar. So we're going to start off with SO3. And to do this, first thing you have to do is count how many valence electrons there are. S has 6 valence electrons, and so does O. So this one's going to have 24 valence electrons. So to draw a Lewis structure, we put our central atom down, and we draw single bonds to all the connecting atoms. Then we load up the outside atoms with electrons until they all have octets, like this. And then we have to kind of massage the molecule to make the central atom have an octet. And we also want to try and optimize formal charges if we can. So for this one, in order to get an octet on the S, we're going to have to make a double bond somewhere in here. And it could actually be on any of these O's, so I'm just going to go ahead and put it on this one. But you could put a double bond here or here. This molecule is going to experience resonance. But this is the completed Lewis structure. There's octets on everything, and formal charges are optimized. So now we have to decipher what the geometry of the atom is. So we see here there's 3 domains. 1, 2, 3. So that means that is going to be a trigonal planar domain geometry. So in fact, it's going to look something like this, more like. And since there's no non-bonding pairs on the S, the molecule is going to have trigonal planar molecular geometry as well. So next thing we have to do is draw the dipoles. So O has a greater electronegativity than S. So we're going to draw dipoles towards all of the O's. Now in order to determine net molecular dipole, we have to add up these dipoles together. And since all of the domains around the S are equal or equivalent, they're all going to cancel out. We're going to get no a molecular dipole of 0. Ergo and therefore, this molecule is going to be nonpolar. So I apologize for the small eraser. But the next molecule we're going to do is OF2. So I'm just going to go ahead and draw the Lewis structure that I already have. Here's your Lewis structure. And since there are there's 4 domains, sorry. Since there's 4 domains, it's going to have tetrahedral domain geometry. So the molecule is actually going to look something a little bit more like this. And then we'll just say this one's coming out, coming kind of out of the page, you know. And this one's kind of going in the page. So this is what your the geometry of the atom is really going to look like. And if we cover up these, we see that it has a bent molecular geometry. So next thing we're going to do is draw our dipoles. F has greater electronegativity, so it's going to be going towards F. And whenever you add these 2 vectors together, you get a molecular dipole that goes down like this. So we are going to have a polar molecule in OF2. Next, we're going to do BeCl2. Lewis structure for this one's going to be a little strange because Be oftentimes is an exception to the octet rule, as it is in this case. So here's our Lewis structure. And there's only two domains, so it is going to be linear domain geometry. So we don't have to draw another picture for domain geometry. And next thing we are going to do is draw our dipoles, which go towards Cl, because Cl has greater electronegativity. And as we can see here, the domains are equivalent. So whenever we add these together, the vectors or dipoles are going to cancel out, and we get a non-polar molecule in BeCl2. Next molecule is going to be CCl4. So I will go ahead and draw that Lewis structure. And as we see in the Lewis structure, there are 4 domains around C. So that means it's going to have tetrahedral domain geometry. So it's actually going to look something more like this. And we just have to imagine one of these two is kind of coming out of the page a little bit, and one of them is kind of going into the page a little bit. So next thing we do is we draw our dipoles. Cl has greater electronegativity, so we draw these dipoles right here. And C has a domain geometry of tetrahedral, like I said, but it also has molecular geometry of tetrahedral because there are no non-bonding pairs, which means all 4 of these domains are going to be equal and equivalent. So whenever you add up all of these dipoles, they're going to cancel each other out, and we get another non-polar molecule. Last one, here we go. Our last molecule is O3, which is a little quirky. It experiences resonance as well, so this double bond in your Lewis structure could be drawn here. But what we see from drawing this Lewis structure is that there's 3 domains around the O, which means that's trigonal planar domain geometry. So this is going to be more like what the domain geometry is going to look like. And since the domains are not all equivalent, see we have oxygen on a domain, oxygen on a domain, and a non-bonding pair. Since these are not all equivalent, we're actually going to get a net molecular dipole that goes down like this, basically because it has a bent molecular geometry due to the lone pair on the trigonal planar domain geometry. So we finish up with this, a dipole pointing down like this, making O3 a polar molecule. Now, some common mistakes people will make is drawing the Lewis structure incorrectly. Not following those basic steps and just kind of throwing something off, which will throw off your whole problem. And not getting the geometry, the domain and molecular geometries right. That's a common mistake as well. So I hope you all learned something, and I will see you in class on Wednesday.